Section 1 Introduction. In this introductory section, we're focusing on large language models, LLMs, like Llama, which typically have a preset limit on the number of tokens or chunks of data they can handle at once, often capped at 2048 tokens. In many scenarios, such as in lengthy conversations, document summarization, or long-term planning, this limitation can pose a problem. Hence, there is a desire for LLMs with a larger capacity, but the challenge is that training these models from scratch can be resource-intensive. This situation prompts the question, can we expand the context window, the amount of input data the model can consider at once, of an existing, pre-trained LLM? One method is to further train an already trained transformer model with a larger context window. However, our experience shows that this approach is rather slow in adapting to a larger context window. Even after more than 10,000 batches of training, the model's context window only expanded from 2048 to 2,560 tokens, which indicates this is not an efficient method for significant expansion. Certain techniques such as Alibi and Lex allow transformers to be trained on shorter context windows and then apply that training to larger ones, but this isn't universally applicable. Many pre-trained LLMs, including Llama, use positional encodings that don't extrapolate well. This limitation restricts the ability to use these techniques for extending the context window sizes of such models. To overcome these limitations, we propose a method called position interpolation for extending the context window of existing pre-trained LLMs, including Llama. The fundamental concept is to downscale the positional indices to ensure the maximum position index aligns with the previous context window limit during the pre-training phase. In simpler terms, we modify the positional encodings at nearby integer positions to allow for more input tokens, unlike the previous method which could lead to extreme and unpredictable values. We have theoretically validated our approach, showing that the interpolated attention score, a key calculation in these models, has a much smaller upper limit, making it far more stable. We have also found that position interpolation is highly efficient and effective in practice. After a brief period of fine-tuning, the model can adapt to significantly larger context windows. We've tested this approach with Llama models, expanding the context window from an initial 2048 tokens to up to 32,768 tokens. The results demonstrate that position interpolation can easily enable very long context windows with negligible costs compared to pre-training. Furthermore, these extended models maintain good performance even for tasks within their original context window sizes, albeit with minor performance degradation on certain benchmarks. We also discovered that position interpolation-based models could effectively utilize the much extended context window and showed a steady reduction in perplexity, a measure of how well the model predicts a sample, with the increase of the context window. We applied position interpolation in a long text summarization task and observed competitive results. This work also validates a prior hypothesis that transformer models can extend beyond their original training sequence lengths. We propose that the previously known difficulty of extending to longer sequences may be largely due to direct extrapolation of positional encodings, a problem that can be significantly alleviated by using our approach of interpolating position encodings instead. We also acknowledge concurrent work on the same issue, notably a blog post called Superhot that also utilizes positional encoding interpolation to extend the context window. Fine-tuning with another technique called LoRa also appears to work well, as discussed in online forums and repositories. Our paper further extends the context window using position interpolation and provides a theoretical explanation of why interpolation yields more stable results than extrapolation. Section Summary. In this section, the authors discuss the challenge of extending the context window of large language models, LLMs, and propose a method called position interpolation. Instead of extrapolating the position encodings, which can lead to instability, position interpolation downscales the position indices to match the previous context window limit. The authors demonstrate that position interpolation is highly effective and efficient, allowing for the extension of the context window up to 32,768 tokens with minimal fine-tuning. The extended LLMs show improved performance in text modeling and long text summarization tasks, while still maintaining good performance within the original context window sizes. Section 2 Method. Let's dive into our methodology. Firstly, we'll touch on the background of rotary position embedding, or ROPE, which is used in transformer models like the Llama model. Transformer models need a specific method to keep track of the order of inputs, and that's where positional encodings, like ROPE, come in. So, let's understand ROPE. Imagine we have a position index that falls between 0 and a number c, and an embedding vector, which is just a list of values, x. This embedding vector has dimensions according to the attention head, which we'll label as d. Now, ROPE takes these and defines a complex function, involving both the position index and the embedding vector. Without going too deep into the math, the function takes pairs of values from the embedding vector, treats them as complex numbers, and multiplies them by an exponential factor related to their positions. This method uses the imaginary unit, denoted as I, and a scaling factor theta. Now, how does this function relate to self-attention score, which is a crucial part of the transformer model? Well, the self-attention score is simply the real part of the product of this rope function for two positions, which we'll label as m and n. And crucially, the score only depends on the difference between the positions, mn, which is determined through trigonometric functions. The rope is applied to both query and key embeddings at each layer of the model to calculate the attention scores. However, rope has some limitations when it comes to extrapolating or predicting for larger contexts unseen in the training. In other words, when we try to extend the model to handle larger context windows, the perplexity, a measure of uncertainty, can become extremely high, resembling an untrained model. 4. Instance, if the model is trained on a context window of size L equals 2048, we'd hope that it could work reasonably well on longer contexts, but it may not fully utilize information appearing beyond L if we pose a question at position 3000. The model, trained on a maximal window size of 2048, won't be able to consider evidences provided at position 0, but should still use the evidences at position 2900. However, the model tends to fail dramatically in this case. Even if the evidence is close by, at position 2900, the model often fails to answer the question at position 3000. One might wonder, if the attention score decays with the relative distance, why does the model struggle with questions at distant locations? This decay implies that content from far away shouldn't matter that much, right? Well, it turns out the decay bound can still be quite large, depending on certain values, and isn't as limiting as we might expect. Consider the trigonometric functions used in the model as basis functions. These are the building blocks of other functions. Our self-attention score could be viewed as a sum of these basis functions, multiplied by some complex coefficients. Now, the problem becomes clear. While the self-attention score may be small for the range we've trained on, it can give huge values outside of this range. This is because these trigonometric functions, with a large enough dimension, can approximate any arbitrary functions. Hence, there are always some combinations of the coefficients, which are linked to the key and query, that can result in small function values in the trained region but much larger values beyond. Section summary. The method described in this section introduces rotary position embedding, ROPE, as a position encoding technique for transformer models. ROPE uses complex trigonometric functions to define vector-valued embeddings that capture relative positions. However, while ROPE's attention scores depend on relative positions, its extrapolation performance is poor, leading to high perplexity when extending to larger context windows. This is because the upper bound on attention decay derived in a previous section is too loose, allowing for large values that affect model performance beyond the desired context window. Section 2.3 Proposed Approach, Position Interpolation, Pi. In this section, we propose a new approach called Position Interpolation, Pi. The main concept here is to stabilize the process of interpolation to prevent erratic values. We achieve this by avoiding the extension of attention scores to values greater than the maximum context window, denoted as L. Instead, we introduce a new attention score, (a)s, that scales the original attention score in relation to the ratio of L and a larger context window, L'. To give you an idea of how this works, we substitute our original function f, used in ROPE, with a new function f', which rescales the arguments of f. Essentially, we are reducing the position indices from a range of 0 to L', to a range of 0 to L. This aligns with the original range of indices before applying ROPE. This adjustment makes it easier for the model to adapt as the maximum relative distance between any two tokens is now reduced from L' to L. We ensure that the range of position indices and relative distances remain consistent before and after extension, thus offsetting any potential impact on attention score computation caused by changes in the context window. The effectiveness of our method is highlighted in Theorem 2.1, also referred to as the interpolation bound theorem. It suggests that the interpolated attention score behaves well and is effectively constrained. In essence, the theorem shows that the difference between our interpolated attention score and a linearly interpolated score will not exceed a specific boundary. The boundary value depends on a variety of factors, including the maximum magnitude of our complex coefficients, h, and the natural logarithm of a constant, c. This linear interpolation is based on two grid points that we know behave well, and it is enforced by LLM pre-training. If we know the attention score behaves well on integer grid points S1 and S2, we can interpolate any value between these 2 points. It's worth noting that our approach of rescaling position indices doesn't necessitate any changes to the model architecture or introduce any additional weights. This is advantageous as it allows us to retain the original optimization and infrastructure of the model even after extension. Following this process, we can fine-tune the model using a next token prediction task on an extended context window size, using a pre-training corpus such as the pile. This process generally only requires tens to hundreds of thousands of examples, and we've found that the results are not particularly sensitive to the choice of these examples. This is likely because during this phase, the model is simply adapting to the new context window rather than learning new information. To further decrease the interpolation and extrapolation boundary, we could consider applying a regularization technique to the query key product magnitudes during LLM training. One possible method is ridge regression with proper regularization. This could potentially reduce or even eliminate catastrophic extrapolation errors. However, this approach has yet to be explored with current LLM pre-training techniques and remains an interesting avenue for future work. Section summary. The proposed approach, called position interpolation, PI, suggests using an interpolated attention score instead of extrapolating it to longer context windows. This interpolation reduces the maximum relative distance between tokens and improves the stability of the attention score computation. The interpolated attention score is shown to be well behaved and more stable compared to the extrapolated one, without introducing extra weight or modifying the model architecture. Additionally, fine-tuning the interpolated model using the next token prediction task can further improve its performance. Section 3 Experiments. In this section, we delve into our experiments. We present compelling evidence that position interpolation effectively amplifies the context window up to 32 times the original size. This enlargement can be accomplished with just a few hundred training steps. The resultant models are robust language model learners, LLMs, that can effectively utilize extended context windows. We exhibit its effectiveness across a range of tasks, including language modeling, Passkey retrieval, and summarizing lengthy documents. Moreover, we provide benchmark results of these augmented models on the original Llama evaluation benchmarks. In terms of our setup, we modified the pre-trained 7 billion, 7B, 13B, 33B, and 65B Llama models to have context windows of up to 32,768 in size. We achieved this either through direct fine-tuning or using the position interpolation method. Aside from adjusting the position indices for the models extended with position interpolation, we did not make any modifications to the original Llama models. To elaborate on our training procedure, we fine-tuned all model versions by predicting the next token. We utilized the Atom W optimization algorithm with beta 1 set to 0.9 and beta 2 set to 0.95. We adopted a linear learning rate warm-up of 20 steps, commencing from 10% of the maximum learning rate. We set the learning rate to 2E5 for the 7B and 13B models and to 1E5 for the 33B and 65B models. We did not apply any weight decay. For enlarging the 7B, 13B, and 33B models to a context window size of 8,192, we utilized 32A100 GPS and a global batch size of 64. For all other scenarios, we employed 128A100 GPS and a global batch size of 128. The primary reason for using a larger number of GPUs is the memory limitation during fine-tuning, but it's feasible to use fewer GPUs in certain scenarios. We trained all our models using PyTorch with fully sharded data parallel and flash attention. Unless mentioned otherwise, for the position interpolation method, we fine-tuned the models for 1,000 steps. For direct fine-tuning, we used 10,000 steps. Our primary fine-tuning was done using the Pile training dataset. We also compared the fine-tuning performance on the Red Pajama dataset in a subsequent section. Section summary. In our experiments, we demonstrate that position interpolation can significantly increase the context window size up to 32 times the original size with just a few hundred training steps. We show that the resulting models are strong language and learning models, LLMs, with fully effective long context windows, and we evaluate their performance in various tasks such as language modeling, Passkey retrieval, and long document summarization. Additionally, we provide benchmark results of the extended models on the original Llama evaluation benchmarks. Section 3.2 Long Sequence Language Modeling. In this section, we evaluate how well our expanded models and some baseline models perform in long sequence language modeling. We use two datasets for our tests, the book corpus known as PG19 and a clean dataset of mathematical proofs from Archive. We test these models on specific subsets of the datasets. For PG19, we use all 100 documents in the test split. For the proof dataset, we take a random selection of 128 documents that contain at least 32,768 sentence piece tokens and limit each test document to the first 32,768 tokens. We then calculate the perplexity at varying context window sizes, using a sliding window approach with a stride of 256. From our results, we discovered that models improved significantly in their perplexity when extended using our method, especially with larger context window sizes. For instance, with an increase in context window size from 2048 to 16,384, we observed reductions of perplexity ranging from -0.14 to -0.5 for various llama models. This demonstrates a consistent trend that our models generally perform better with larger context windows. This improvement suggests that our models can effectively use these larger windows to better predict upcoming tokens in language modeling tasks. Moreover, we found that this improvement continues with even larger window sizes of 32,768, particularly in the PG19 dataset for the Llama 7B and 13B models. This suggests that our method might enable these models to be extended to even larger context windows. However, when we extended models using the direct fine-tuning method, we saw either a regression, increases in perplexity of up to +0.48, or minor improvement, reductions of up to -0.12, at larger context window sizes. This shows that models extended in this way have a limited ability to use context windows larger than their pre-trained settings. On occasion, we noticed a small decline in perplexity for our extended models at the original context window size of 2048. For example, in the proof dataset, there was a degradation ranging from 0.01 to 0.05 across all models extended with position interpolation. This minor drop in performance within the original evaluation context window was expected, as position interpolation might negatively impact the language model's performance due to forcing position encodings to reside in a narrower region. We also examined the relationship between perplexity and the number of fine-tuning steps for the Llama 7B model when it was extended to 8,192 and 16,384 context window sizes using position interpolation. This was evaluated using the PG19 dataset. Interestingly, without any fine-tuning, the model still showed some capability in language modeling, as indicated by a perplexity less than 20 for extending to an 8,192 context window. However, with fine-tuning, we noticed that the perplexity improved rapidly. For instance, just after 200 steps, the models had already exceeded the original model's perplexity at a 2048 context window size. This implies that the models were getting better at using sequences longer than those used in pre-training for language modeling. By 1,000 steps, the models had shown steady improvement and achieved significantly better perplexity. Section summary. The authors evaluated the performance of their extended models and baselines on two datasets, PG19 and cleaned archive mathproof. They found that their models achieved significantly improved perplexity with longer context window sizes, indicating their ability to effectively predict next tokens in language modeling tasks. In contrast, models extended via the direct fine-tuning method showed limited capability in utilizing longer context windows. Additionally, the authors observed a minor degradation of perplexity within the original context window for their extended models in some cases. Section 3.3 Measuring effective context window size through Passkey retrieval. In this section, we explore the notion of the effective context window size in our extended models. This term refers to the furthest distance a given piece of data can reach and still be effectively interpreted during the inference process. To determine this, we adopt a synthetic evaluation process known as Passkey retrieval, which was suggested by prior research. In this process, the models are asked to find a random Passkey that has been hidden within a long document. You can refer to figure for a visual representation of the document format. We estimate the upper and lower limits of the effective context windows in a certain way. Let's imagine the random Passkey is positioned k tokens away from the input's end. If the model repeatedly fails to find the correct Passkey across several separate attempts, it's an indication that the effective context window size of the model is smaller than k. However, if the model repeatedly succeeds in finding the correct Passkey, we can infer that the effective context window size of the model is at least k. We tested this on the 7B and 33B variants of the Llama model, which were extended either through position interpolation or direct fine-tuning. For each model, we used 32 different k values that were evenly distributed within the targeted context window. We ran this test 10 times for each k value, and for each trial, we used a random 5-digit Passkey. In our results, we reported the maximum k value, k_max, for which the model had a success rate of at least 20% for all k values up to and including k_max. We observed that the models extended via position interpolation successfully reached their target extension objectives in terms of effective context window sizes. This was signified by the effective context window size reaching the maximum value of k_max after only 200 fine-tuning steps. This was consistent across both the 7B and 33B model sizes and up to 32,768 context windows. In contrast, Llama models extended via direct fine-tuning only demonstrated a minor increase in the effective context window size, from 2048 to 2560, even after more than 10,000 fine-tuning steps. There was no clear sign of a fast increase in window size. Section summary. The effective context window size, which refers to the maximum distance a token can effectively attend to during inference, is measured through a synthetic evaluation task called Passkey retrieval. By testing the ability of models to retrieve a hidden passkey in a document, we can estimate the upper and lower bounds of the effective context window size. The results show that models extended via position interpolation consistently achieve their desired extension objectives in terms of effective context window sizes, while models extended via direct fine-tuning only see minimal increases in window size. Section 3.4 Benchmarks on original context window size. In Section 3.4, we discuss the performance of our models, enhanced by position interpolation, using the standard benchmark tasks set within the original context window size of 2048. A table outlining the evaluation results is provided for reference. It can be observed that the extended models, adjusted to 8,192, yield equivalent results when applied to the original benchmark, initially designed for a considerably smaller context window. The dip in performance on these benchmark tasks is up to 2% for both 7B and 33B model sizes. Furthermore, as the context windows lengthen, there is a slightly greater regression on the benchmarks. However, this remains within acceptable boundaries for the majority of tasks. Interestingly, the choice of fine-tuning datasets doesn't appear to greatly impact benchmark performances. This could potentially be due to the minimal number of fine-tuning steps incorporated in our methodology. The benchmark's regression aligns with the findings from our perplexity regression, which is detailed in a separate section. In Section 3.5, we shift focus to long document summarization. Here, we gauge how our models perform when faced with this specific task. We make use of the GovReport dataset, which comprises 17,457 training documents and 972 evaluation documents. Each document comes with a summary that has been created by a human. We shorten all input documents to only their initial 15,000 tokens. Our models, enhanced by position interpolation and the Llama extension, are fine-tuned with a context window of 16,384. This step still necessitates the rescaling of position indices. The raw document is initially formatted using the template depicted in a figure. Then, the prompt is amalgamated with the corresponding ground truth summary, limited to 1,000 tokens, of each document. Over the span of 10 epochs, the model is fine-tuned using the next token prediction task based on this setup. Any losses stemming from the input prompt proportion of training examples are not included during our fine-tuning. To generate a summary of each document in the test set, we use a generation temperature of 0.5 and a text top p proportion of 0.95. These parameters help manage randomness and variety in text generation. The final output is cut off at 1,000 tokens. To evaluate the model's outputs against the actual summaries, we use 3 evaluation metrics: Rouge 1, Rouge 2, and Rouge L scores. A table showing our evaluation results is provided. Additionally, we've compared our outcomes with those from 2 baseline models in the existing Scrolls leaderboard. Overall, our models, with a context window of 16,384, yield competitive R1 scores with very minimal hyperparameter tuning. This implies that our models can effectively handle the task of long document summarization. Section summary. The models extended by position interpolation were evaluated on standard benchmark tasks with a context window size of 2048. The results showed that models extended to 8,192 produced comparable results with a slight degradation of up to 2% on the benchmark tasks. Additionally, the models performed well on the long document summarization task, achieving competitive Rouge 1 scores compared to other models on the Scrolls leaderboard. Section 4 Related Work. Here's a simplified version of the Section 4 Related Work, Enhanced Language Learning Models. Some studies have improved language learning models, LLMs, by adding modules that retrieve related documents and incorporate the findings into the LLM's input context. Our research builds on these works by increasing the context window size to include more documents. Our approach maintains the original attention mechanism and model structure, making it versatile for tasks beyond just retrieval, like summarizing long documents and few-shot learning. Recurrent and memory transformers. Other research has added memory capabilities to transformer models through recurrence, which enhances their ability to handle long sequences. However, these methods only allow attention to a simplified version of past inputs, which might limit the model's ability to remember specific details. Unlike these, our model attends to all previous tokens without simplifying, preserving all details, but at a higher computational cost. Approximated multi-head attention. There's a significant amount of research aimed at reducing the memory and computational complexity of the multi-head attention (MHA) mechanism through approximation or sparsification. While this work doesn't directly use these methods, our approach is compatible with most of them because our changes only apply to position encodings, not attention mechanisms. Length extrapolation. Some recent studies aim to train transformer models on short sequences and use these models on longer ones. But these methods haven't been applied to some of the largest language models. Our work focuses on extending the use of existing LLMs, which could significantly cut down on pre-training costs. Interpolation. The technique most similar to ours comes from a study on vision transformers. The authors proposed to linearly interpolate learned position embeddings to support higher resolution, which would increase the number of input embeddings. Our approach differs in several ways. We interpolate position indices rather than embeddings. We've successfully extended the context window up to 32 times their length, and we've evaluated the effectiveness of position interpolation for extending context windows specifically for language models. Furthermore, we speculate that a similar method could be directly applied to LLMs with learnable position embeddings, and we plan to investigate this in the future. Section summary. One line of work extends language models, LLMs, by incorporating retrieval modules to include related documents in the input context. Our approach complements these works by allowing even more documents to be included in the input, making it more versatile for tasks beyond retrieval. Additionally, while other works use recurrence or memory mechanisms to handle long sequences, our method allows full access to all previous tokens without compression, although it comes with higher inference costs. There is a large body of research focused on reducing the memory and computational complexity of the multi-head attention mechanism. Although our method does not utilize these techniques, it is compatible with most of them since our changes are limited to position encodings, not attention mechanisms. While recent research has explored training transformers on short sequences and inferring on longer ones, our work focuses on extending existing LLMs, which saves pre-training costs and preserves the quality of the original models. We differ from a related technique proposed for vision transformers by interpolating position indices instead of embeddings, exploring a larger upper limit of context window extension, and confirming the effectiveness of position interpolation for extending context windows in language models. In conclusion, our results, along with previous work, provide empirical evidence of transformers' ability to handle significantly longer sequences. We also plan to investigate the applicability of a similar method in LLMs with learnable position embeddings in the future.